Post-tensioning introduction and growth in the U.S. building construction. This presentation reflects my experience primarily over the 40 plus years in the U.S. and worldwide, specifically in the U.S., being interested in a practice of post-tensioning, in its growth and in its design. Now, I will start by giving you an outline of the post-tensioning, advent of post-tensioning worldwide, early application in the U.S. building construction, early software-based design, because I believe availability of software helped greatly in the growth of post-tensioning, then finite element approach to design of post-tensioned structures, and the maturity in design and construction. The advent of post-tensioning is attributed to Doring in 1988, who obtained a patent in Germany for pre-stressing slabs and used metal wires. The objective at the time was control of cracking. In 1920s, Freycinet introduced the well-known and widely accepted Freycinet hardware shown partly on the right. The hardware simplified construction and led to increased application of post-tensioning. Now, the design of post-tensioning was very different then. It is also very different today, the European style. Then the focus of the application was in bridge construction, heavy structures, and the reduction of tension stresses or avoiding tension stresses in the extreme fiber. The design was using, based to my view, complex diagrams, all targeted to determine where the post-tensioning has to be placed and how much, so that in service condition it will not cause cracking, or if it does cause cracking, the crack width will be acceptable. The diagram you see on the right is a typical design diagram for a post-tensioned member. Target was crack control. Extreme fiber stresses were calculated under different loading conditions and tendon profiles. Early application in the US, however, is different. Not much happened, neither in concept nor in design procedure between 1920 and the mid-1950. In mid-1950s, innovative building contractors in the US used pre-stressing strands and rods in flat slab construction to control deflection and cracking for thin concrete slabs. The strands were greased and paper wrapped to reduce friction at stressing. The objective was deflection control and to some extent cracking, primarily deflection control. What you see on the right is an example of early construction where the tendon is where the steel, pre-stressing steel, is greased and paper wrapped. The construction technology in concept and application widely differed from the European-based practice, very different. The US application was the introduction of unbonded construction technology, as opposed to the European practice, which was based on grouted post-tensioning. In the European grouted system, the void between the pre-stressing steel and its conduit subsequent to stressing was filled with grout. The US practice was mostly focused on thin slabs, unlike the European practice, where heavy members were target of post-tensioning. The development of simple stressing jacks and simple anchors, as shown on the right, attributed to Edward Rice, helped simplifying the construction and growth of its application. This contributed to promote the application of single-strand unbonded tendons. The design was later taken over by Atlas Corporation in California that helped greatly in expansion and promotion. In early 60s, T.Y. Lin introduced the load balancing method for structural design of post-tensioned members. Now, the load balancing method, the concept and design of the structure rested on commonly familiar concepts that structural engineers knew. The load balancing method introduced by T.Y. Lin viewed the pre-stressing as an upward force, similar but opposing to the member's self-weight. If this is the post-tensioned member, this tendon was viewed to apply an upward force, as I have shown in here, to counteract the weight of the structure, and that force obviously included downward components as well as axial forces. The reduction in effects of self-weight from post-tensioning, as shown in here, now in effect the downward and upward result in a reduction of the load on the member from what it was before. So the reduction in effects of self-weight from load balancing reduced deflection and cracking. The simple load balancing method was readily adopted by the structural engineering community and led to increased application of post-tensioning in building construction. In 1976, Clifford Fryermuth formed the Post-Tensioning Institute. He formalized the practice of post-tensioning in the US through many technical publications and educational seminars. While the contribution of post-tensioning technology in Europe is fully acknowledged, it is recognized that the development of post-tensioning in the US for application in common building construction took place independently from the European concepts and practice. Here, I like to emphasize the word independently, both in concept and in practice. Now, we are still talking about early applications. Continued developments of the hardware for single-strand stressing, from paper-wrapped all the way to what we have today, pushing through an enlarged hose, overlapping it, and they extruded, all helped in development of the unbonded system into something we have today, durable and easy to construct. Over the following decades, the hardware matured to durable and easy to use alternative. Now, early designs in 50s were based on the intuition of innovative contractors. I like to emphasize it was based on contractors' intuition. The objective was reduction in deflection and cracking. The practice was then fine-tuned by observation of its outcome. Much of this legacy of intuition-based practice is still the backbone of ACI 318 perspective design of concrete floors. Uplift from profile post-tension tendons was simply viewed to reduce the self-weight of the member, with other requirements and design algorithms remaining essentially unchanged. We are talking about early practice in the US. The practice worked well. Why? Since the tendon amount and arrangement strictly followed proven example. The practice was based on examples of successful projects. The layout recommended was essentially similar to what I have here on the image. Here, groups banded in one direction and distributed in the other. The recommended tendon arrangement and the detailing of ACI 318 prescriptive design method for column-supported floors today remain the legacy of the tuition-based practice of innovative contractors of the past. Now, what happened then? Let us start with early 80s. When I started at VSL in California, there were already 2 commercially available software for design of post-tension floors. Both were based on modeling, analyzing, and designing design strips extracted from the floor at hand. The computer we were using then was typically something like this example, Wang computers, which were different from the large computers, and consulting engineers could afford to have Wang computers and do their programming on them. And that is, so to say, the first computer that I was encountered to use and program when I started work at VSL. Dissatisfied with underlying assumptions of the available software, I initiated the development of the software ADAPT, which at the time was jointly owned by VSL and myself. I was working at VSL, and there was a contract that the software developed by me will be owned by VSL and myself and will be jointly marketed. That is early 1980s. Shortly, I joined San Francisco State University in pursuit of my former profession as a professor of civil engineering in Iran. In Iran, I used to teach, but the practice was interrupted in Iran because of the revolution we had in 1978. Florian Barth, a former colleague at VSL, joined me when I moved to San Francisco State, joined me to form ADAPT Corporation. ADAPT Corporation located in San Francisco. The firm was located in San Francisco, very close to San Francisco State University, where I had my office. The focus of the firm was the design of post-tension structures. Florian Barth took charge of the consulting aspects of the business while supporting the environment of continued development of ADAPT software. In late 1970s, the advent of computer-based design in consulting firms led to development and design of software for post-tension floors. It had already started in late 1970. Now, the software-based design in 1970s and early 80s when I joined VSL followed the established simple load balancing concept. The practice remained rooted on simple load balancing until 80s, when the shortcomings in design technology were corrected and the introduction of the extended load balancing and its implementation in ADAPT became clear. This is an image which is on the top right, trying to highlight the practice based on simple load balancing. In simple load balancing, maybe the next slide will better explain. The extended load balancing recognized that pre-stressing force eccentric to members centroid, such as shown in the figure above right, this force and this force do not line up. In the figure shown, they create additional bending in the member and should be accounted for along with other actions. The practice of design did not account for the available software, did not account for. The only force from post-tensioning that the practice accounted for was the upward force and a uniform pre-compression, irrespective of the fact that the tendons were at times did not line up at the anchors. Early let us talk about early based software tools. Interestingly, around mid-1980s, a group of force-sanctioning engineers were gathered in Denver to discuss and decide, among other topics, whether non-collinear tendon forces result in bending moment additive to those introduced from tendon uplift. What am I trying to convey? The engineers were gathered, among other issues, to decide whether, if the forces do not line up, are not collinear, does it create a bending moment or does it not? That was the question at the time. The consideration was significant since prevailing practice of the time did not recognize the presence of moments. The design engineering community needed clarification. Clarification in the sense that whether this force and this force offset by M will create a bending moment shown here. Interestingly, the question was put to vote. The majority confirmed that the ADAPT software accounting for the presence of moment from tendon eccentricity is the valid application. It was recommended to be adopted for design. It was recommended, the vote said, was confirmed that MP exists and is part of the actions to be accounted for. The affirmative vote led to the wider application of ADAPT software and propelled its extensive development. Now let us talk a little bit about the early software application, early software-based design tools. The initial releases of the software were based on isolated single design strip as shown here, taking a line of columns along with the tributary of the columns, slab tributary, extract it from the floor system, analyze it separately. The software recognized, modeled, and allowed. Good. The software recognized, modeled, and allowed for the intricate geometry of the design strip as shown as on the right. An example of it is on the right. The software is today available also. It recognizes all the complex changes and accounts for them in modeling and design. The development of ADAPT PT continued over the years to make it the widely worldwide use of design tool for a single strip. Apart from the US, it features the major international building codes like the British, the European, the Canadian, Indian, Australian, and so on. ADAPT PT, now owned and marketed by RISA, is still the primary software for design of force-tension members using strip method. Now, it's interesting here, in regards to the development of simpler hardware, it is interesting to note that the initial release of ADAPT in early 1980s and beyond used copy protection software that I have shown here. This one is a Coke, let us see, and each user had to use something, a piece of hardware that I'm holding in my hand, something like this. This piece of hardware had to be inserted in the computer so that the computer could run the program. Early protection devices had this. Later developments in a computer made it simpler. Now this was the second generation, which is much smaller. It is called half board, and this had to be installed, as I have at the image bottom right, in the box of the computer so that the computer could run the program. Now, later, with the developments, I'm trying to find later in the developments, the next generation was something like this small one, which I have on the top right of the image. Top right of the image. This did not have to be inserted inside the computer. It could be attached to a port on the box outside, which was a great help. And obviously, there has been a lot of development, and now we have this was the next generation, something very, very small for copy protection. It had to be inserted in the USB port, but now RISA has, so to say, software licensing. Everything is done remotely through software. You don't have to go through all this, but it is interesting how much the protection has improved. Now we are talking about the early based design scheme. In 1980s, I recognized that load balancing method of design could not handle the structures where deformation control governs the design. Now look here, in this segmentally constructed bridge, the two ends, when they meet, they have to be aligned. You have to work hard during the construction to make sure that they line up at the end. Likewise, in this cable stay bridge, the two tips, when they meet, they cannot be offset more than a limited tolerance. So deformation during the construction is critical. So the design of such structures must be based on detailed recognition and accounting for both non-prestressed and prestressed reinforcement in service condition for deformation control, because rebar also is important in amount of deformation in service condition. To address the shortcoming, I developed the parallel post-tensioning analysis and design software ADAPT ABI for incremental construction and deformation control of post-tensioned members. Where deformation control during the construction is a major construction presence, the presence of PT tendon in location and amount, as well as rebar in location and amount, are governing parameters to be accounted for. This is in addition to consideration of time-dependent creep, shrinkage, tendon relaxation, all come into the picture for deformation control. This diagram is intended to illustrate what is the difference between what was then and primarily is done based on load balancing or its concept, and what is the other scheme which I have outlined in chapter 8 and was the basis of ADAPT ABI. Here, if you take a piece out, the tendon is not removed, is there. Whereas in load balancing, on the left, the tendon is no longer there. It is substituted by the forces. So as the member develops, the presence of both rebar and tendon can become impacted by the deformation, because deformation of the member deforms the rebar, deforms the tendon, and that in effect changes the geometry, impacts the geometry. But the other one is different. You substitute the force by the force of post-tensioning, by forces at the centroid, and the forces essentially remain unchanged. Anyway, this is explained in presentation 8, in case you were interested to know more about it. Then, at the same time, in early 1980s, I met Alan Bommer on a post-tension project in Seattle. I found Alan Bommer an exceptionally bright and competent engineer, knowledgeable in post-tensioning concepts. Later, Alan started composing the computer program Floor, which is now concept. Floor concept is the first practical finite element program intended for the wide application design of concrete floor slabs, either conventionally reinforced or post-tensioned. Floor concept is the first finite element program, and that has to be attributed to Alan Bommer to have initiated the first practical finite element program for design of concrete floor slabs, either conventionally reinforced or post-tensioned. Later, Alan and I formed a joint effort in the development and marketing of the program. Here is an image from the program. The background of the program was based on the concept of considering tendons as an applied force in service condition and resisting force in safety condition. That was the basis, which is an extension or a fashion of load balancing, again explained in presentation 8 in greater detail. Alan proved to be technically very competent and a fair partner. The collaboration continued for several years. Nurturing a conceptual difference in treatment of post-tensioning in design, then I started the development of the finite element program Adapt Builder for design of post-tensioned and conventionally reinforced floors. Adapt Builder was coded on the concept of tendons as well as rebar being considered as resisting members in both in-service and safety state of members' response and design. The concept, again, I'm repeating myself, is outlined in presentation 8. The consideration is illustrated in the simplified view of a flat shell element used in the software. You have the flat shell element through which you have a number of tendon segments and a number of rebar segments. In the general case of a floor finite element shell, there are several tendon segments as well as rebar segments that pass through the element. The stiffness matrix of the element accounts for the presence and contribution of each tendon and rebar segment at the location and orientation that each pass through the element, both in service and safety state of the floor. The formulation recognizes that in service, the local impact of tendon force on the encasing concrete element is the friction and possibly lateral force between the tendon and the concrete segment, not the axial force. Maybe here I have to pause a little bit. Maybe I have to come up with another presentation. Today, the intuition-based mechanics of solids rests on the belief that if a tendon is passing through an element, there will be force of tendon transferred from the tendon, or the force of tendon here comes to the segment. Now, in reality, for service, when we talk about the cracking, crack width, temperature cracking and shrinkage and so on, the force of the tendon is delivered to the structure at the anchors, at the edge of the slab or wherever the anchor is. The force of the tendon distributes into the structure based on the geometry of the concrete structure, where its openings are, where the beams are. So the pre-compression, which we talk about when it comes to crack control, is the result, primarily the result of the force of a tendon applied at the anchor. What in service condition, what we have through here is really the friction. The friction between the tendon and the concrete is the force transfer between the two. Now that is difficult to convince my colleagues, but that's where it is. The tendon axial force passes through the captured tendon segment. I see. What I say here is the axial force from here just passes through. The friction between the sheeting and the concrete is the interaction of the force. Obviously, there is Pre-compression, which comes from the anchor, force at the anchor. The tension force is applied at the tendon anchor. I'm repeating myself, bear with me. Generally at the edge of the slab. I jumped ahead. The tendon force is distributed in the slab based on the geometry and stiffness of the concrete floor. The concept was successfully implemented and tested in the 2D program ADAPT ABI. The implementation of the concept for a flat plate is too complex. Each slab shell element consisted of combination of elements, chunk of concrete that encases, that the concrete that is encased in the shell, rebar and tendon segments. Each component is recognized in its position and value and is expressed at the element nodes. By the way, what I just said a little while ago was for service condition when we are talking about crack control. When it comes to safety, it's a different story. Of the contribution of tendon to safety is a different story. And also, if the tendon has curvature along its length, there will be forces which the tendon exerts in addition to its friction between the tendon and the member arising from the curvature. So I just wanted to be clear that nothing is missed. In addition, for deformation in service condition, each bar or tendon segment deformed under the load deforms under the load with allowance of creep, shrinkage, and relaxation. Alejandro Eraso, a talented and sharp engineer with strong conceptual understanding of mechanics, a classmate of my son Florian at Stanford University, developed the formulation and its implementation in the stiffness matrix of ADAPT Builder software. To include all those contributions in this flat shell and bring them all to the nodes here so that the system stiffness matrix could be compiled and later to map them back to each individual. That was a tough job, and Alejandro Eraso managed to handle it. Then Pavel Stankiewicz, also a strong structural engineer and software expert, led the successful coding and testing of the finite element concept adopted in ADAPT building software. Whatever Alejandro did, Pavel Stankiewicz, along with the help of others, coded it and tested it in the program to make sure that it all works. The fully tested capability of the software that is based on comprehensive design concept was not released commercially to the public at large. We had limited release. The limited release was based on the belief that from the commercial standpoint, the consulting engineers at large were more interested in simple solutions as opposed to the comprehensive approach which calls for in-depth knowledge and greater appreciation of positioning technology. The commercial release of the comprehensive software was limited to ADAPT ABI, which was used successfully in many bridge construction, segmentally bridge, and cable stayed bridges. Now I want to draw your attention to a couple of other items which I think are significant in analysis but are not apparent to the end users. The features that are not apparent to the end users, but critical to the authenticity and accuracy of the software outcome. Now, the adapt builder model of analysis model is based on the physical geometry of the structure, not the prevailing analytical geometry. Now, what do I mean? If this is the physical geometry, typically in the background, the software uses this model to represent this. There is a node here which is common between the two. To keep common nodes, there is a change in geometry. Adapt does it like this. In other words, keeps the physical geometry exactly as is in real structure, so the nodes do not match here. This obviously has to be taken care in the formulation for handshake between the force here and here. The reason the nodes here are common is for handshake of the force. The analysis, the member-based model, this is the member-based model shown in C, is used. That is in Adapt Builder and Adapt ABI, where slab, beam, and columns extend to the full length and connect for transfer of force as in the physical space. Now, in order to account for the presence of each tendon and rebar, and that was necessary because the model accounts for presence of each tendon and rebar in the model and its contribution to deflection, to cracking, to strength. Now, where am I? In order to account for the presence of each tendon and rebar in the amount and the location, each occurs, the structural system where each occurs, the structural system was expressed and solved in a virtual analysis space here. The solution of this was carried out here. The nodes in the analysis space are here, and each one of them had its contribution transferred to here for analysis, and after the analysis was completed, the actions and the deformation were mapped back to real location and reported to the user. The solution obtained is mapped back to the physical structure for display and reporting of the structure. Now, all that was analysis, but as far as visual goes, Nicolas Mangon designed the architecture and wrote the code for the visual creation and display of the Adapt Builder. As far as creation side is concerned of the model, like what you see on the right, Nicolas did all the work. Nicolas' work included the presentation of each tendon and each rebar in the model from the creation of the model. But then once it comes to creation, it is transfer of it into a system matrix. And once it comes to the system matrix and solved, it comes the question, now what? How to get the results out in the manner and shape that the end user wants. And that is where somebody else came into the picture. That is what Florian Alame did, which I'll talk later. So Nicola's work included also the breakdown of the model into design strips. The work subdivided the floor model into design strips and design sections. Lijian Gong joined ADAPT later, and for over 20 years, Lijian coordinated the coding of the different components of the program to make sure that they all can speak together and work together to conclude with a solution. That again was not simple because the software is made up of several components in multiple languages that needed coordination and smooth interaction. And as I mentioned here, for over 20 years, Lijian did all that work very efficiently and very successfully. Another critical consideration was the finite element discretization of a floor, as shown on the right. The discretization was based on the recognition that shape, size, disposition, and connectivity of the finite element cells have impact in the solution, the accuracy of the solution. Well-proportioned quadrilateral elements sensitive in size and shape to the local complexity of the structure. Wherever there is complexity in geometry, then the elements have to be accordingly adjusted. Additionally, all force transfer was to occur at the nodes of the elements for full compatibility. Starting from a basic mesh generation formulation, Shahram Taravi, former teaching assistant of my daughter Shireen in a structural engineering course at Stanford University, joined ADAPT and developed the organic refined meshing of the structure, which is sensitive to the geometrical intricacies of the physical structure. Shahram managed to create this irrespective of the complexity of the geometry, floor, steps up and down, openings, changes in thickness, beam, recognized beam, and created a proper mesh for beam where there was a slab, proper mesh for slab, and put it all correctly together. He did a very good job. In addition, local cracking, crack width, and post-crack deflection are among design considerations of the European and a number of other international codes which had to be taken account. In other words, in ACI we have a limit on extreme fiber tension stress. You do not exceed it. But in other codes like EC2, European code, and other codes, some of the other codes, it is permissible to allow cracking provided you control the width of the crack. The width of the crack is controlled based on the application of the floor. Shahram also developed a formulation for the initiation of cracks, crack width, and its impact on deflection. The images show the loss of second moment of area from local cracks. For example, here the moment about the up-down axis MYY results in loss of second moment of area in the amounts shown here. Yellow means there is no loss, and what's happening here? Yellow, there is no loss, and then here I have the maximum maximum 31% loss, where you have this color in one direction and then in the other direction, and this loss in local stiffness obviously results in increased deflection as well as results in cracking and the crack width calculation. So the loss in second moment of area is reflected in the stiffness of the affected finite element cell, followed by new solution. Coming back now to what happens after the system matrix is solved and you get results. What you get results is just deformations, but to convert that into a user required information, such as what is the capacity, what is the demand, how much reinforcement, where it meets code and where it does not meet code, is a totally different story and a lot of information, which not only you need to go back into the finite elements to extract all that is necessary, also you have to know the code to know where an item is satisfied or not satisfied. There, Florian Alamy, my son, focused on extraction of post-tensioning and presentation of the analysis and design outcome from the raw finite element results in a format that best suit the end user engineer to complete the design. As an example, at each design sections, these green lights, this is a support line, and these green lines are the design sections. At each design section, using the user-defined reinforcement, if any, because sometimes users put a mesh and that is taken into account in the design, and added required reinforcement by this software, the software displays the demand values. These are the demand values. Demand in negative moment, demand positive moment with let me start. Demand value, the black is the demand based on the geometry and the load. This is the demand. The program shows the demand along with the capacity from the existing post-tensioning, computed post-tensioning, and existing rebar. So where the demand, which is shown in the black here, falls outside the capacity, obviously it shows in a different color and then rebar is added. In addition, Florian led the graphical presentation team beyond the prevailing practice and developed Visicon. Visicon displays in 3D the adapt builder analysis model with authentic details of its physical features, including pre-stressing. Visicon detects conflict in construction, if any, at design stage. It also can display the post-tensioning and physical features and construction steps of software models developed, created by other software. In addition to Adapt Builder, that is what I just said, Visicon handles data presented by other models. As expectations from authentic modeling and analysis results shifted from computer-based visualization to cloud-based cloud computing, Florian led the creation of TrueBuild, which is a cloud-based modeling. TrueBuild, a cloud-based software, displays the construction steps and details of a building construction created by Adapt Builder or other software, along with analysis and design results. Let us not forget, this is a post-tensioning presentation, so TrueBuild does take authentically the presence of post-tensioning in location, in amount, and in display. That is not forgotten. Now, coming to the end, let me just recognize individuals who helped. From Florian Barth, supporting the environment for development of Adapt well over 40 years ago, to its transfer to resale by Florian Alami in 2020. I benefited from the contribution of more than 100 talented individuals in the creation and prominence of Adapt software. I am grateful to them all. In 2013, the American Concrete Institute, ACI, recognized the Adapt contribution as outstanding engineering development work to concrete design and construction by conferring to Adapt the Charles Whitney Award. This recognition really goes to the 100 plus people who helped over 40 years to create this software. So, in summary, I talked about advent of post-tensioning, early application in the US, early software-based design, talked about finite element-based, analysis models, visual validation, that is Visicon, then recognition. Thank you for listening. Additional information you can find in this book.